Welcome to General Chemistry Mini Lecture Series, Lecture 34, the Bohr model and quantum theory. First, let's take a look at electron transition in Bohr's model. Electrons can only have specific amounts of energy. We call that quantized energy. What does it mean? You see, this is the energy from low to high. Electrons can only have energies at, for example, n equals 1 level, n equals 2, or n equals 3. It cannot have energy, let's say, somewhere between 2 and 3, or between 1 and 2. That's why electrons' energy are quantized. You only find electrons on those orbitals. You cannot find electrons between those orbitals. That's why electrons don't have energy between n equals 1 and n equals 2, as I just talked about a while ago. The energy of electrons is proportional to the distance between the orbitals and the nucleus. So the lower the n, the lower the energy. Now we'll talk about absorption. What is absorption? So when electrons jump from orbitals with lower energy to orbitals with higher energy, energy is absorbed. And this process is called absorption. The electrons are excited. That's absorption. The opposite electron transition is called emission. So electrons emit radiation when they jump from an orbital with a higher energy to an orbital with lower energy. In this case, energy is released. For example, fireworks, you see the beautiful colors. That's actually the energy released in radiation form. And different colors represent different amount of energy. The distance between the orbitals determines the energy of the photon light produced. The energy required for this absorption is determined by the two energy levels, n equals 1 and n equals 3. Similarly, the energy released between this transition, that is determined by the distance between these two energy levels. So when light passes through a prism, a pattern can be seen, and that pattern is called an emission spectrum. This is actually hydrogen emission spectrum. So what you can see here, that's the wavelength. Lower wavelength, which means higher energy, that's with a violet radiation, and then higher wavelength, which means lower energy, so you have a kind of orange reddish light here. Please note that there are only 4 lines can be seen, and all of those dark places, there are no radiation. Okay, then why do we see those 4 specific wavelengths in hydrogen atom? That question was answered by Rydberg. So he analyzed the spectrum of hydrogen and developed an equation for calculating the specific wavelength of those electron transitions in hydrogen atom. Once you plug in the n values, for example, for this absorption, the lower number of n is 1, and then the higher number of n is 3, then you will find out the wavelength of the radiation responsible for this absorption process. You can do the same for this electron transition that causes this emission. In this case, the N low is 2 and N high is 3, then you will obtain another wavelength value, and that is the radiation responsible for this specific emission process. This is a better illustration. Here is the nucleus. So we can consider electrons' energy here is close to 0. So this is the n equals 1 orbital. That actually should be a circle. N equals 2, another circle, and so on and so forth. And those 1, 2, 3 should be equivalent to those 1, 2, 3. Okay, so they are the same. So which means with a higher n number, the energy is higher. So therefore, you see, that's the energy axis can go any direction because this is a circle. Lower energy and higher energy. Lower energy, higher energy. I didn't draw that axis here, then that will be lower energy and higher energy. Okay? So now let's take a look at this line, this orange or reddish line. Okay, take a closer look. That was resulted by the emission. You see, emission that's so from higher energy to lower energy, then energy is released. Okay, so now let's take a look at that. This energy difference or energy release or energy emitted, we can call that delta E 3 to 2. The transition is from n equals 3 orbital to n equals 2 orbital. That's why I call that 3 to 2. And this delta E carries a wavelength of 656 nanometer. That's this red light. That's why you see this red light. You don't see a light with 658 or 670 because there are no such orbitals that can cause that emission. Similarly, if electron is transferred from n equals 4 to n equals 2 in a hydrogen atom, so that delta E is actually larger than this delta E. Okay, so therefore the wavelength should be shorter. The higher the energy, the shorter the wavelength. This violet line has the largest energy. That's why it has the shortest wavelength. Now it's time to work on example 1 in lecture 34. We have an electron transition from n equals 3 to n equals 2. We want to find out the wavelength in hydrogen spectrum for the emission that is resulted by the transition from n equals 3 to n equals 2. We need to use the Rydberg equation. This is the Rydberg constant, and then 1 over n low square subtracted by 1 over n high square. And n low in this case is 2. Therefore, that should be 2 squared. And n high here is 3. So therefore, the 1 over lambda equals 1.524 times 10 to the 6, 1 over meter. Then we should be able to find out lambda, that is actually 656 nanometers. Now let's take a look at the spectra of additional elements. This one is the continuous spectrum, which means, like the daylight, sunlight, that should contain all of those wavelengths in the visible region. That's why you see different colors. Again, violet color that has a higher energy, shorter wavelength, and the red color should have lower energy and longer wavelength. So this is hydrogen we just talked about, and this is sodium. You see also very few lines, but they have different wavelengths. than the hydrogen atom. And we have a calcium, maybe more lines, but still not a continuous spectrum. Okay, here is mercury. Again, why you have those specific lines? Because electrons' energy are quantized. In previous slides, we already touched the energy change when electrons transition from one orbital to another orbital. And now this is the equation for calculating that energy change. Nf here is the orbital after electron transition, and Ni is the orbital before electron transition. If your answer is a negative, that means energy is emitted. It's an emission. And positive means energy is absorbed. That should be absorption. Let's work on problems involved emission and absorption. So we want to find out the energy associated with these two electron transitions. The first one is from n equals 5 to n equals 2, and you can see that's high energy to low energy. Then that process should be an emission process. We use this key equation. Just need to pay attention to which n value is Nf and which one is Ni. So for the first question here, the Nf is 2. Nf is 2, therefore 2 squared. And Ni is 5. So you just simply carry out this calculation within the parentheses. That's a positive 0.21. Therefore, the answer for the first transition is a negative. Therefore, that's an emission. Now the second one, from low energy to high energy, that's an absorption or excitation. All right, but let's take a look. Again, we apply the same equation, but now Nf is 4, Ni is 3, and this should give us a positive energy change value, 1.06 times 10 to 19 joules, because this energy change is positive. So therefore, this transition corresponds to an absorption process. Electromagnetic radiation, it behaves like particles, is because of photons. Photons are particles, of course, very small, tiny particles. But how about other particles? Do other particles also have the wave nature? Yes, actually, de Broglie proposed that particles could have wave-like character. The wavelength of a particle is inversely proportional to its momentum. M times v, that's momentum. M is mass, v is the speed of the particle traveling, or velocity. We call this equation the Broglie equation. Let's work on a de Broglie wavelength related problem. We need to find out the wavelength of a 2.7 grams ping pong ball traveling at 35.8 miles per hour. Write down the h first. You may notice that I'm using different units for Planck constant, but actually this is the same as joule. So I change the unit joule to this unit in order to be able to cancel the unit involved in this calculation. M mass, as you can see, in the Planck constant here, we have kilograms, but in this question, gram is a unit for mass. So therefore, we need to convert 2.7 grams to kilograms. That's m. And now, v is the velocity, 35.8 miles. Let's work on the numerator of the velocity first. 35.8 miles. Do we see miles here in Planck's constant units? No, we see meters. 1 mile equals 1609.34 meters. And then the denominator in the velocity, that's hour. We need to convert hours to seconds so that the seconds can be cancelled. 1 hour is equivalent to 3600 seconds. And now you can see grams are cancelled, kilograms are out, hours are out, seconds are cancelled, miles are cancelled. There's only one unit remaining, which is meters. So here's meter squared, here's meter. Then we just have meter left. And that should be the unit for the wavelength. Now we know the wavelength for this ping pong ball traveling at this speed is 1.53 times 10 to negative 32 meters. Now we will go over complementary properties as well as uncertainty principle. We already know that electromagnetic radiation as well as electrons, they possess both wave-like nature as well as particle-like nature. But if we try to observe the wave nature, we cannot observe the particle nature of electrons, and vice versa. Therefore, we say the wave and particle nature of the electron are complementary properties. If we know more about the wave nature, we know less about the particle nature, or vice versa. This is the uncertainty principle. Delta X is the uncertainty in position, where you can find electrons. What is the electron's location? So that's the X. Then delta X is the uncertainty in position. When you try to observe the position of a given electron, that's like an experiment. Then the experiment always have some errors. So therefore, delta X is the error in measuring the position of electrons. You may say that. Delta V, this is the velocity, not the frequency, okay? Delta V is the uncertainty in velocity. The product of the two can never be zero. It's always greater than zero. Actually, not only greater than zero, it's always either greater or at least equal to h bar over 2m. m is the mass of the particles. And h bar is the reduced Planck constant. Basically, it's Planck constant divided by 2 pi. The uncertainty principle means that the more accurately we know the position of a small particle, the less we know about its speed, and vice versa. In other words, we cannot accurately measure both the position and the velocity of a small particle like an electron. Now let's see the difference between determinacy and indeterminacy. In classical physics, the movement of particles can be determined by the particle's velocity, position, and forces acting on it. This is actually called determinacy, meaning a definite and predictable future. On the other hand, according to the uncertainty principle, the one we just discussed in the previous slide, we cannot know both the position and the velocity of an electron. Therefore, we cannot predict the path. This is called indeterminacy, meaning an indefinite future. Then how do we describe electrons in atoms? The best way we can do is to use quantum mechanics and wave function to predict the probability an electron will be found in a particular region. The best wave function to describe the electron movement is the time-independent Schrödinger equation, a wave function. H psi equals E psi. H is just an operator, and psi is the wave function, and E is a constant that equals to the energy level of the system. Many of the properties of atoms are related to the energies of the electrons. That's why it's important we have the energy in Schrödinger equation in this wave function. For an electron with a given energy, the best we can do is to describe a region in the atom of high probability of finding it, called an orbital. As we talked about previously, when we discussed uncertainty principle, we could not accurately know both the position and the velocity of electron. But with the help of this wave function, we can locate a region where we can find the electrons with very high probability. And those regions are called orbitals. Orbitals means the path electron moves. The orbital is important now here. The size, shape, and orientation in space of orbitals, they are determined by three integer terms called quantum numbers in the wave function. And we will go over those quantum numbers in lecture 35. These are the end of lecture 34 quiz questions. I will see you guys in lecture 35, quantum numbers and electron orbitals.